a particularly interesting type of motion, and it's interesting to see how forces play out when they're going around in circles. Now, I've mentioned before that you can have a constant speed, but not constant velocity. And the case where we spoke about that was when an object was moving around in a circle, and that is what is meant by uniform circular motion. We're moving at constant speed in a circle. The speed is unchanging, but if you take a circular path, at this point the velocity may be off in this direction. Then you go around here, and at this point the velocity is this direction. Your velocity vectors are always going to be tangent to the circle, and so those velocity vectors are changing direction, and because they're changing direction, the velocity is changing, which means there is an acceleration. The acceleration is quantifiable, even though it's not quite as simple as doing delta V over t. But the derivation is pretty complicated. It involves vectors, and so I'm not going to waste your time with that, but I will direct you to this video that I found. There is a link to this on RenWeb as well, but I'll just write out the link here too, just in case anyone who's not in my class is watching this on that off chance. This is a good explanation of how to derive the centripetal acceleration formula, the acceleration of an object moving in a uniform circle. But it comes out that for an object moving in a circle, it is referred to, that acceleration is referred to as centripetal acceleration. And we use A for acceleration, subscript C for centripetal, and that comes out to V squared over R, where R is the radius of the circular path, and V is that constant speed, whatever it may be. And going along with this, knowing that F equals ma, we can say centripetal force is mass times centripetal acceleration, which is mv squared over r. Now, I would like to pause here and point something out. If you have an object moving around in a circle, there are different forces acting out. There might be gravity. If say you have an object on a string, there might be a tension. Here there might be gravity. If a car is going around a curve, there's friction, there's gravity, there's normal, and all those forces would add up. Centripetal force is not an additional force that you add to those. Centripetal force is a net force pointing toward the center of the circle. So you may, depending on the scenario, you may have gravity plus tension equals centripetal force, but you'll never say, oh, well, I've got gravity, I've got tension, I've got friction, and I've got centripetal force, and I need to add these all up. Okay. Centripetal force is a net force. The acceleration pointing toward the center of the circle, let me just make a quick statement about that. If you do the derivation, you can see where that comes from, but if you think about this, according to Newton's first law, at this point, an object would tend to keep going off in a straight line, right? But it's being pulled off that straight line, and that's happening by its velocity changing, in this direction. That velocity that is being pulled toward the center of the circle, and that's what's pulling it off this straight line path and into this curved, circular sort of path. It's the same thing that happens with planets as they orbit around there. They would tend to go in a straight line, but then gravity pulls them off their circular path off of the straight line path into an orbit, and that's what puts them into that circular motion. In that case, centripetal is caused by gravity. In the case of you got a ball on a string and you're spinning it around, the centripetal acceleration is caused by tension, but then there would also be gravity when it's up at the top, and then it would be tension minus gravity down here because the gravity would be pointing downward. the car on the road, the centripetal acceleration is primarily being caused by friction. But just keep in mind, centripetal is a net force. It is not a force that you add up as part of the sum of the forces when you're doing Newton's second law. Okay. So other forces add together to produce that centripetal force. You may also have heard about centrifugal force. Centrifugal force is something that it is centripetal force, but it's what centripetal force becomes when you move into a rotating reference frame, and that's a little bit more complicated than we're going to deal with. So for our purposes, there will never be a centrifugal force. Although we will talk about something called a centrifuge, which is something that will separate out chemicals and stuff like that. So if we can just take a simple example. Let's say that we have grams attached to a string, whirled in a uniform circle, radius 6.5 centimeters, completing one revolution every 0.75 seconds. What is the centripetal force acting on the weight? Well, we know centripetal force is mv squared over r. We have mass, we have radius, we need velocity. What we do know is that we have one revolution every 0.75 seconds. A velocity is a distance over time. One revolution is kind of a distance, but one revolution is 2 pi r. One turn around the circle, this is the circumference of the circle, is 2 pi r meters per revolution. So that's 2 pi times 0.065, sorry, over 0.75, not 0.075, goodness. So that's about equal 128, what? Oh, I mistyped here. I put 2 pi divided by 0.065 times divided by 0.75. 128 doesn't make any sense. That's where you stop and think about it. 128 meters per second for an object going around in a circle. Not very reasonable. 0.54 meters per second is our velocity. So then our centripetal force is 1.2 times that 0.54 over the radius 0.065 squared. I punch that in, times 1.2 divided, not 1.5. I'm having calculator issues this morning. 0.065 squared. Comes out to a centripetal force of about 154.66, said so forth newtons. Okay. In this case, it's whirled on a string, so that string is probably what's providing this centripetal force. So that's just one example of how we could do a centripetal force problem that we could do. Let's look at another example. As I said, it's something that spins around and separates out different substances that might be in a solution. So if you have a centrifuge that rotates with a speed of 102 meters per second, centrifuges go really fast. The bottom of the test tube is 9.1 centimeters from the axis of rotation. What is the centripetal acceleration at the bottom of the test tube? This is very straightforward. Centripetal acceleration was b squared over r, so that's going to be 102 squared over 0.091, and I can punch that in, and this is going to be a very large number. Holy Nelly, 11, 4, 3, 2, 9. That might actually be too fast. 0.6703, etc. meters per second squared. 102 meters per second might be a little bit unrealistic. But that's how you would go about the calculation. That number seems awfully large to me. Yeah, but that's just another example of how we can apply the centripetal acceleration formulas. I want to make one comment about centripetal acceleration. If you've ever been, I don't know if you've ever been on the little spinning playground toy. I think is it a merry-go-round? I think it's called a merry-go-round, where people stand on it and then it spins around and you kind of fly off and whatnot. Now you feel like you're flying off the edge, right? But I've told you that centripetal acceleration is pointing toward the center of the circle. So what's really happening is that there's friction between you and this toy, and maybe some force from where you're holding on to to it somewhere. And that is providing an inward force that is pulling you toward the center of the circle. The reason you feel like you're going to fly off is that as this is, let's say this is spinning around, this way. As this is spinning around, you would tend to go off in a straight line according to Newton's first law. And that straight line path would cause you to go flying off of the toy. So that's why you feel like you're being pulled toward the outside. You're actually tending to go in a straight line, and it's just that straight line velocity that makes you feel like you're being pulled toward the outside. So that's how the physics sort of works there.